Now let's do problem 4. So here's problem 4. It's basically just a true-false question. So let's just get right to grips with it, starting with this first one. So if the limit as x goes to 5 of f is 2 and the limit as x goes to 5 of g is 0, so I'm going to put some marks here just because it makes me talking more exciting. So f is going to 2 and g is going to 0, then what is the limit as x goes to 5 of their quotient? Okay, so g is going to 0, right? The denominator is going to 0, and the numerator is going to some non-zero number, real number. Okay, so that means that the limit is not defined. So it does not exist is right. So the answer to A is true. Okay, and what about B? B says if f goes to 0 and g of x goes to 0, then the limit as x goes to 5 of the quotient does not exist. And this one actually is false. Alright, so let me give you an example of a case where it does exist. Okay, so consider something like this. So sine of 0 is 0, and so what happens to this thing as x goes to 5? As x goes to 5, this turns into sine of 0 over 0. Okay, but we've seen this function a few times. This is supposed to be the graph of y equals sine x over x, okay? And this thing is not defined at 0 because if you plug in 0 you get an undefined number, 0 over 0. But the limit makes perfect sense. The limit approaches 1 from both sides, and so the limit for this thing as x goes to 5 would just be 1, okay, which is a perfectly good number. So just because f and g go to 0 doesn't mean that their quotient doesn't exist. Okay, and so let's go on to C. So what do you think about C? It says if p is a polynomial, stupid graph thing. If p is a polynomial, then the limit as x goes to b of p of x equals p of b. Now I think if we were in class, everybody would be shouting that yes, this is true, because what this is saying is that p is continuous. Remember the definition of continuity? So this says that p is continuous, and all polynomials are indeed continuous. Okay, so this would be true. Okay, and now for D it says if the limit as x goes to 0 is infinity and the limit as g of x goes to 0 is infinity, then the limit of the difference is 0. And so in fact infinity minus infinity is not 0. So let me just write that. So there's no real number infinity, but it's kind of true that infinity minus infinity is not 0. In fact, infinity minus infinity can be whatever you want. And I think I give an example of, right? Yeah, here where I say it's false. This is an example. Okay, so look at what happens here as x goes to 0. Okay, as x goes to 0, both this goes to infinity, and this also goes to infinity. If you look at their graphs, you'll see that there's a double-sided asymptote going up to infinity for both of those as x goes to 0. But if you look at what happens to their to this, okay, so here I evaluate the limit as x goes to 0. You put them over a common denominator, and then you can see, I don't know if, just plug values in your calculator or something. I don't want to get bogged down on why that goes to infinity, but it does. So the limit as x goes to 0 of those things is infinity, right? So this claim that it always goes to 0 is false. So this is a false statement. It doesn't always go to 0. I just gave an example where it goes to infinity. So the answer to D is false. And both E and F are questions about the intermediate value theorem. And that was an interesting thing for my computer to do. So remember the intermediate value theorem. The intermediate value theorem says basically if you have a dot down here and you have a line and you have a dot on the other side of the line, and you continuously connect them, then there must be some point where you cross the line. Okay, so that's the intermediate value theorem. So this is saying that if f of 1 is less than 0, if f of 1 is greater than 0, so let's draw a picture of that, and f of 3 is less than 0, so here's it being less than 0 over at 3, then there exists a number c between 1 and 3 such that f of x equals 0. So that would be true if we had also had the hypothesis that f is continuous. But look, there's a discontinuous counterexample. So here's f, it makes a leap here across the line, right? And so this is a counterexample. So E is false because there are discontinuous functions that don't satisfy that condition. Okay, and now f is also about the intermediate value theorem. It says if f is continuous and f of minus 1 is 4, so let's draw a picture of that. Here's minus 1, and f of minus 1 is 4, and f of 1 is 3, which we'll just draw as being a lot lower. Then there is some number r between negative 1 and 1 such that f of r equals pi. So what I'm drawing here in this horrible orange color is the line y equals pi, okay? And so this f is continuous. And so the intermediate value theorem applies. So there's no way to continuously get across this line without touching it. And so what happens when you do that? You get some r here, and it turns out that f of r is pi, because it's what's happening to the input r is getting sent up height pi, right? So f of r is pi. So the answer to f is true. All right, and so that's how you do this problem.